So sample space is listing all the possibilities of something. Sometimes we need a diagram. Sometimes we use a tree diagram to show a sample space. So if you roll 2 dice, you could represent that with a chart. I've highlighted one dice in yellow and the other one is not highlighted. It's like imagining I have a red dice, a red and a white one. Now, inside of here, inside of the red, are all the sums that are possible. And it gives you a sense that, you know, something that you might know, rolling a 12 is harder than rolling a 7. That might seem obvious because the only way you can roll a 12 is a 6 and a 6. But a 7, there's so many options. And one of the things in these options is that a 5 and a 2 happens twice. Does that make sense? Especially if you have 2 different colors. I could roll a 5 on the red dice. Oh, if that actually worked out, that would have been amazing. But no. I could roll a 5 on the red dice and a 2 on the white dice, or I could roll a 2 on the red dice and a 5 on the white dice. So the 7 could happen that way. There's no way to get a 12 in 2 different ways. Right? You can't get a 6 on the red dice and 6 on a white dice, or 6 on the white dice, 6 on the red dice. That's not different. So that only shows up once on our chart. So now we can use this to find the probability. Remember, probability is how many times something happens out of a total. So how many times are there 6? There's 6 of them out of 36. Oh, sorry, 5 of them. 1, 2, 3, 4. Can't count today. 5 6s out of the 36. Your chance of getting a 6 is 5 out of 36. Your chance of throwing a double. Count all the doubles. There's 6 of them out of 36. How many are less than 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 36. And here is where words become really important. That word there, scoring more than 8 or scoring an even number, this is, we want to find the probability of greater than 8, or is this symbol. This is how we could write that out. Yes. Less than 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is a good question how I got 11 when there's only 10 of them. There you go. Good. I'm glad you recounted it. I wonder how I counted it wrong. You know what I did? I know exactly what I did. Okay? I went 5s, and I counted 4 of them. And I said, I'm done counting 5s, and in my head I had the number 5. After counting 4 5s, I had 5 in my head. Then at 3 more is 8, 9, 10, 11. That's exactly what I did. Right? How did I do the double one? 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s. So this would be the notation to write probability greater than 8 or even. And so what does that mean? Take out my highlighter here. Greater than 8 would be in yellow. Even, I'm going to do in green. And 12, thank you. Okay. How do we do that? Well, I could just count the ones that are highlighted once or twice, just count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24. Get 24 out of 36. I could have counted my yellow ones, counted my green ones separately, and then subtracted the ones I counted twice. That's using the formula. But remember that or means it's in one or the other. If this question had said scoring more than 8 and scoring an even number, then my answer would only be 4 of them have been highlighted both. So that word and or can really change the question. So we have to really pay attention to those kind of small details. In an experiment, a coin is tossed and a dice is rolled. Draw a sample space for this experiment, and then find the probability that on a single experiment you obtain a head and a number less than 3. So we could set up a chart for this. On one part, you have the numbers on the die. On the other, you have heads or tails. If we set up that chart and have the complete sample space, less than 3 and heads are circled in red. So our probability would be 2 out of 12. This is one way that we can show our sample space. We could also show our sample space with a tree diagram. In a tree diagram, you choose one thing to happen first. Here we roll the dice. You get 1 through 6. Then, flip the coin after. Each branch represents something. So here's heads in 1. Here's tails in 1. Here's heads in 2. There's tails in 2. And you could list your sample space that way. Either way, you get 12 in total. And as a result, 2 of them have heads and are less than 3. So the probability becomes 1 out of 6. Next definition. Probability has a lot of definitions, and the IB questions will want to make sure that you understand the definitions. 2 definitions that often get confused are mutually exclusive and independent. Mutually exclusive means they can't happen at the same time. Independent means that one does not affect the other. Okay? Here's a good example of 2 things that are independent. I've got a coin here. What are my chances of getting heads? 1 out of 2. I didn't get it. Okay? I'm like, oh, I didn't get heads. I want to try again. I'm going to increase my chances by rolling a 4. Now I'm so much more likely to get heads than before. Does that make sense? No. Does rolling the 4 have any effect on me getting heads? Could I get a 4 and heads at the same time? Yes. You could still have both events happen. But I can't flip this now and have a better chance of getting heads. So 2 events are independent if the occurrence of one does not affect the other. Now there's some people that believe that I just flipped a heads. Now, what's the chance of getting heads? Is it less because I just got one? No. I got tails. I got tails again. Now I've got tails twice in a row. Do I have a better chance of getting heads now? Or is it still 50%? Still 50%. Okay? But, oh, I got tails again. 3 times in a row. Oh, failed. Now, there are people, though, this is a common misconception in probability, that if I got tails 10 times in a row, they all of a sudden think, now you have a better chance of getting heads because it's bound to happen. Well, it's still 50% at each time. In fact, we could do this. Let's say we say we're going to do an experiment. We just need the whole world to volunteer. And we're going to give one person $1 million. That's the winner. Okay? Round 1, you have to flip heads. So everybody flips, and they look. If you got heads, you're on to round 2. 6 billion people are playing this game. Chances are around 3 billion are going to get cut out of the first round. Okay? Round 2, you get to stay in if you get heads again. Flip the coin. Chances are half the people are going to get canceled out, but half the people are going to keep going. About. Not exactly half. Okay? How many rounds do you think you could play? Well, not infinite. I don't think someone's going to flip it in. Eventually. But like you started with 6 billion, probably round 1 would cut you down in half. That's what probability would say. 3 billion. Then down to 1.5 billion. Then down to 7.5 million people. Then 3.75 million people. Then dividing by half gets harder. And then, yeah, right? We would keep going. But eventually, they would run out of people. But at the same time, there would be someone who would get heads like 20 times in a row, which is really, really rare. But it is possible. But each event is independent. So, dice is rolled, coin is tossed. These are independent because one does not affect the other. Here's a product rule for independent events. Probability of A and B is equal to the probability of A times the probability of B. What are my chances of flipping the coin and getting heads and rolling a 4? Well, the heads probability is 1 out of 2. Getting the 4 is 1 out of 6. Doing them together would be 1 out of 12. Does that make sense? You got a 50% chance here, a 1 out of 6 chance here. Having them both happen is going to be a 1 out of 12 chance. So card is drawn at random, and you roll a dice. Find the probability the card is the jack of spades and a 5 is thrown. 1 out of 52 for the jack of spades, 1 out of 6 for the 5. Your chances are 1 in 312, which isn't very likely. But if you did this with 600 people, someone might win. Not guaranteed, though. And that's some of the math that we're going to start to look towards. Like, what are the chances of something happening when you're looking at multiple events? Right now, we're just getting the basics. Here's one for you to try. Bag contains 3 red marbles and 2 white marbles. Another bag contains 1 red and 4 white marbles. You take a random marble from each bag. What's the probability both are red? The marbles are different colors. And at least 1 marble is white. I'm going to check how you did. So Notation-wise, we want to find probability of red and red. In this case, we would have a product rule. Drawing out of one bag doesn't affect drawing out of the other bag. So these events are independent. So it would equal just the probability of the red one times by the probability of the red one. In the first bag, the probability of the red one is 3 out of 5. In the second bag, it's 1 out of 5, giving us a total probability of 3 out of 25. How did you do? Okay? And so A shows a good example of where we can do it just using a formula. You are going to find that drawing a tree diagram or a sample space for independent events can be really helpful. Okay? What's happening here? We're drawing a marble out of bag 1, and then we're drawing a marble out of bag 2. So if we wanted to draw this situation out, here's our bag 1. You could get red or white. And then you go to bag 2. After drawing out the red one, you could get another red or a white one. After drawing out the white one, you could get a red one or another white one. With a tree diagram, you can also show the probabilities on the branches. So getting a red one out of the first one was 3 out of 5. Getting the white one was 2 out of 5. In the second bag, the red one was 1 out of 5, and the white one was 4 out of 5. 1 out of 5, and 4 out of 5. For question 1, we were looking for red and red. There's only one branch that shows that. The reason the tree diagram is really helpful for B is, can you see that there's 2 cases to get different colors? So the mistake that students make in B is they just go, I want probability of red and white. But you could also get the probability of white and then red. On our tree diagram, we can see that there's 2 situations. You could get red and then white, or you could get white and then red. 12 out of 25 plus 2 out of 25 gives you 14 out of 25. So now for part B, we were looking at this one, red and white, and this one, white and then red. Now for part C, there's 2 different ways you can logically think about this one. Just add this here. You could either say at least one marble is white. Can you see that there would be 3 cases on our tree diagram that show that? The white and white, white and red, red and white. You could add all 3 of those together. So option 1, the longer option, is you do white and white plus white and red plus red, then white. I'll label this above: white, 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 red, red, white. If you add those all up, you get 22 out of 25. That's option 1. Whenever a question says at least, sometimes it's easier to count the opposite. What's the opposite of at least one white? No white. No white would be 2 reds. If you take, so here's option 2 for solving this. If you take 100%, which is 1, and you subtract the red ones, which we figured out was red, red, I'll put above this 100%. Well, 25 out of 25 minus 3 out of 25 will also give you 22 out of 25, and there's less calculations to do. Okay? And that can be important for something like flipping a coin, right? Flipping a coin once, 1 out of 2. Flip a coin twice, 1 out of 2, 1 out of 2. There would be 4 options now. This is your permutations and combinations unit. Flip it again, now I would have had 8 options. Okay? Flip it a 4th time, I get 16 options. My question is, if I flip this 4 times, what are the chances that I get at least one head? My chances would be, you could draw a tree diagram and count them all separately, but the opposite of at least one head would be to get all tails. There's only 1 out of the 16 options that's all tails. So the probability of getting at least one head would be 15 out of 16. I just did it. Did I get at least one head? What would you say, yes or no? If you had to put money on it. You would say yes, because you have 15 out of 16 chance, right? I got all tails. Crazy. Right? Flipping a coin, getting all tails 4 times, 1 out of 16, that seems, oh, that's pretty rare, right? Compare that to winning the lottery, which is like 1 out of 14 million. Ugh, not so good. Yeah, I should just buy 14 million tickets and then you can guarantee to win the lottery, you know, because there's only so many possibilities. You just have to buy every possibility, right? At around 14 million options, at $2 a ticket, it only costs $28 million. But if you want that experience, it's like it's on my bucket list, winning the lottery. You can do it. It just is expensive. Probably cost you more money than you'd win. Let's win the lottery together. Another one for you to try. Here is 4-sided dice. Here's your sample space. I've got some circle things on there to help you. Probability of A and B, did you get 1 out of 16? Okay, because there's only this one that's both of them. Probability of A or B, when you count up all your circles, that's 6 out of 16. You can do the first one. Well, are they independent? Probability of, I don't know if we can say that they're independent. Probability A, the sum of the 2 dice is 6. So if I do that one by itself, probability of A would be 3 out of 16. Thank you. And the probability of both numbers being the same would be 4 out of 16. No, you can't do them as independent events. So the fact that they're different answers, in this case, would show that they're not independent events. Because in this case, so this is a good question. They would be independent events if the situation was roll them, then roll again. But in this situation, what we're looking here is it's just rolled once. And you're looking at the possibilities in rolling it once. If you rolled the situation 2 times, and the question was, what is the probability the sum was a 6 first, and then the second time that both dice were the same, that would be a different question than it just happening once and looking at the probabilities when they just happen once. So in this case, when they just happen once, they're not independent events. Okay? Because, for example, right, if I roll a 1 to begin with, it's impossible to get the 6, but it's still possible to get the double. But if I rolled the 3, I could get both the double and the 6. So there's some problems with doing that separately. And this is where the independent and mutually exclusive sometimes get confusing. I often say that independent usually works, as far as the formulas go, when you have one event and then another event happening after. That's the easiest time to see independence. When something happens the same here, then it's harder. Are these events mutually exclusive, independent, or neither? Okay. If they're mutually exclusive, the probability of A and B should be 0. But the probability of A and B is 1 over 16. So they are not mutually exclusive. And are they independent? If they're independent, the probability of A and B should have been, like we said, multiplied together to get 3 out of 64. But in reality, we found out the answer was 1 out of 16. So they are not independent either. They're not mutually exclusive, not independent, so you would just say that it's neither. There's no special name. They're awkward. No, there's no. Yes?
Is it possible for a situation to be independent and mutually exclusive?
It is not possible. Well, it is only possible. So mutually exclusive means when you multiply them together, you're going to get 0. So the only time something could be independent and mutually exclusive is if one of the things has a 0 chance of happening. So for example, rolling a 7 on a 6-sided die. Very hard to do, quite rare, never happens. You're just rolling one dice, is what I'm saying. Well, it would have to equal 0, and the only way is if one of those events were 0. And if one of the events is 0, there's nothing in it. It's always going to be mutually exclusive with something else.